So here we'll be discussing few more properties of random process. So first let's talk about the Whiteson stationary. A random process x of t is a Whiteson stationary process if and only if the mean, which is the expected value of x of t, is a constant mu x, is a constant over time, and the autocorrelation function Rx of t1 comma t2 is a function of the time difference tau, where tau is t2 minus t1. So the Rx of t1 t2 is just Rx of tau. It doesn't depend on time, but only depends on the difference in time. So strict sense stationary random process have all the moments same, the constant over time. So in communications we only care about the expected value and the power spectral density, which is the Fourier transform of the autocorrelation function. That's why we generally use the Whiteson stationary criteria is enough. We don't need a strict sense stationary because our only required parameters are the mean value and the power spectral density, which we can obtain for any time if a process is Whiteson stationary. So in communications, this is a very important criteria used for all the signals on the noise to model the noise. And next we have the Gaussian process. So x of t is a Gaussian process if and only if x is x equal to the x of t1 so on up to x of t, the vector, the random vector, which is the instant of the random variable x of t, is a Gaussian random vector for any integer k greater than 0 and any set of time instants t1, t2, so on up to tk. So here the random x for any instance of x of t, we get a vector. If this vector is a Gaussian random vector, then x of t is a Gaussian process. So the mean of the Gaussian process is expected value of x, the expected value of this vector. The covariance matrix is expected value of x minus mu times x minus mu whole transpose. So next we have Markov process. A random process x of t is said to be a Markov process if for any time instance t1, t2, t1 less than t2, so on less than tn plus 1. So for all these increasing time instants, the random process satisfies fx of x of tn plus 1 less than or equal to xn plus 1 given x of tn equal to x of xn, comma x of tn minus 1 equal to xn minus 1, so on up to x of t plus 1 equal to x1. This CDF is equal to fx of x of tn plus 1 less than or equal to xn plus 1 given x of tn equal to xn. So what this basically means is, for a random process, the change in state at any time instant only depends on the immediately previous state and doesn't depend on all the other previous states. So here we have x of tn plus 1. Let's consider the next state. This represents all the previous states, x of tn minus 1, so on up to t1. So this is equal to fx of x of tn plus 1 less than or equal to xn plus 1 given the previous state, just the immediately previous state, which is x of tn equal to xn. So this is how a Markov process is defined. Next we have Markov process has a lot of significance because it is used to represent the queuing process and the branching process. It is also used to model the movement of particles. Next we have the strict sense stationary process property. So a random process x of t is stationary or strict sense stationary if and only if for all sets of time instants t1 so on up to tn and any time difference tau, we have f of x of t1 so on x of tm of x1, x2, so on xm is equal to fx of t1 plus tau so on up to x of tm plus tau of x1, x2, so on xm. So what this basically means is the PDF, the joint PDF of the of all the ensembles of the different times, we have it remains constant over time. So basically all the instances of x of t, or for any time instance t1 so on t1, the PDF remains constant over time and doesn't change. So previously for White's and stationary, if the mean is constant and if the autocorrelation is just the difference of time, it's called as a White's and stationary. That's enough criteria for a White's and stationary process. However, for a strict sense stationary process, the definition is quite strict, so the PDF has to be constant over time. Next we have white noise. So WT is a white Gaussian noise process if and only if WT is a stationary Gaussian random process with the properties mu w equal to 0 and the autocorrelation function Rw of tau is equal to mu naught delta of tau. So the autocorrelation function is just an impulse. So if we, as previously said before, if we take the Fourier transform of the autocorrelation, we get the power spectral density, and the Fourier transform of this will give you a all pass filter. So white noise is basically an all pass filter with an all pass filter which has infinite power. So every noise in communication system is modeled using white noise. However, since the energy cannot be infinite, we only take over a certain frequency, so we'll get a noise variance which is finite and not infinite. And next we have the mean ergodic process. So first, an ergodic process. For an ergodic process, all the statistics of let's say of a process x of t, all the statistics which are the first moment, the second moment, so on up to 10 any moment, is same for the ensemble and for the time average, so or the time. So the nth moment of the time and nth moment of the ensemble are same for an ergodic process. However, so for a mean ergodic process, we only care about the first moment. So a White's and stationary process is said to be ergodic in the mean if the time estimate of the mean obtained for a single sample realization of the process converges in both the mean and in the mean square sense to the ensemble mean. So a mean ergodic process is basically if the limit t tends to infinity, expected value of mu x of t, this is the time average and this is the ensemble average. So if the expected value of this tends to 0, then it's said to be a mean ergodic process. So here the mu x of t is 1 by t times integral minus t by 2 to t by 2 x of t dt. This is the expected value along the time. This is the expected value along the ensemble. And we have limit t tends to infinity, variance of mu x of t is also 0. So if these two conditions are satisfied, then we can call it a mean ergodic process.